Okay, so I just want to revisit and explain something again, which I don't think I did too well the first time, but essentially just now explaining how the axes change and how we should think of these axes. Okay, so this is going to be our unboosted frame, or our stationary frame, and I just want to go over again and show you what the new axes are going to look like. So if you remember the boosted axes, I was going to call C, T hat, and X hat. I won't write it down again, but you remember we obtained these from the old coordinates using our Lorentz Transformation. Remember, this is the Lorentz Transformation matrix. And now all this is doing is just performing a linear transformation on both of these coordinate lines. And we can just simply plug in the form of the transformation on some interactive graphing app, and we'll see what's going to happen to these two lines. And then we just remember that this is dependent on our rapidity, or this psi parameter, which is essentially going to control how much boost we're doing to these axes. But now, as I said, what these new axes are going to do, they're going to scissor inwards and become no longer orthogonal. So just drawing for you now the T hat and X hat axes. So these might be one particular set of axes, and the amount by which they scissor inwards is going to depend on this rapidity parameter. But now what I wanted to just re-explain was how we should think of these new non-perpendicular axes, and how we have to kind of change our Cartesian thinking when we deal with these non-perpendicular axes. So if we just consider now Cartesian coordinates, we're going to look at the coordinates of some point P in the space. We know how to assign the coordinates on the Cartesian grid. We just trace out the grid points using a kind of square like this. This is going to be xp, this is going to be tp, the t and x coordinates of this point P. And essentially what we're now doing is we're using a convenient fact of these Cartesian coordinates that basically lines of constant x and lines of constant t are these horizontal and vertical lines respectively. So you should view Cartesian coordinates as a kind of square grid. If, say, this is your origin, then these horizontal lines are the lines on which t is equal to some constant, and the vertical lines, maybe I'll call them constant k so don't get confused with this c. The vertical lines are points on which x is some constant. But now this is going to, and so essentially when we measure the coordinates of a point, we're just looking at where does it lie relative to some of these constant coordinate value lines, and then we can look at its position and we can trace it back to one of these lines, which is going to be at a constant coordinate value, say xp or tp. So hopefully this is a familiar notion, how we assign coordinates in Cartesian or perpendicular coordinates like this. But now this has to change slightly when we move to these non-perpendicular axes. So really the essential idea is going to be the same. We're trying to look essentially what coordinate value this point P corresponds to, and the way we do this is we look at the lines of our coordinates that correspond to a constant value, and then we match up where that point P lies on one of those lines. So for our Cartesian grid, of course, we have these straight horizontal and vertical lines that are at 90 degrees. But now when we move to this non-perpendicular grid, if if I just draw for you now, we're going to have some different kind of grid, which is going to look maybe something like this. And now what we have to realise is that these coordinate squares, if you like, have now been transformed or stretched into some kind of squashed parallelogram shape. And so we can't draw a square to match up where our coordinates are lying because it's going to not correspond to the right line. But now what we need to do is we need to free ourselves thinking about these Cartesian squares, and we need to instead start thinking in terms of parallel lines to each axis. And so what we now have to do is to trace out the, say if we want to work out what the t hat coordinate of this point P is, well we first of all need to realise that this point P is going to lie on some line which is parallel to this t hat axis. And now we should understand this line parallel to the t hat axis. We should now rephrase, this isn't the t hat axis, but it's rather a line on which this x hat coordinate is going to be a constant. So everywhere on these blue lines, the coordinate value x hat is constant. And so if we just look at the point P, we can trace back everywhere on this blue line, the coordinate value of x hat is the same. And so where this blue line intersects our x hat axis, we know that whatever coordinate value here, x hat P, whatever coordinate value this is going to be the same everywhere on this blue line. So it needs to be really clear now that the coordinate value that's the same on this blue line is the x value, not the t value. T hat varies as we move along this blue line, but we're staying fixed in x hat. And then likewise, that's how we would measure the x coordinate of this point. To measure the t coordinate now, we need to draw another line which is now not parallel to t hat, but parallel to x hat. And so we would draw something like this. And we would now realise, okay, everywhere on this red line, the value of t hat is constant. And so whatever this t hat value here is going to be the same as the t hat value over here. So now you can see we've shifted away from the square grid representing our coordinates. We're now using these parallelograms, and we're realizing that the coordinates are going to be measured using these lines of constant x hat and t hat. And so we can see here, just now really kind of roughly and intuitively, this number value t hat of p is going to be a different number value than this t of p, because now just quite clearly from this figure we can already see this interval here, this length t of p is a fixed time interval, but now that fixed time interval is going to be longer than this length in the t hat frame. The t hat interval is simply this interval here. Because we're measuring along a single coordinate axis, we can kind of associate these, or we can match up now these Euclidean distances. But that's just a bit of a taster. What we're going to be able to see now is that these, when we start talking about relativistic physical effects, we're going to be able to read off some quite nice quantities like this from a diagram like this. But I just wanted to go over and restate how we measure points in these new kind of non-perpendicular coordinates. So we have to remember that our coordinate grid is being stretched and shifted as well. And so rather than thinking about points as lying on these kind of squares where we can conveniently trace back their coordinate points, we need to be a bit more careful and realise we have to be measuring against the lines of constant coordinate value. And so just in Cartesian coordinates, these are conveniently placed to be at 90 degrees, and so we can just simply read off from a picture like this. But when things become non-perpendicular, we need to be a bit more careful that we're measuring in the right direction. So this was just an extra comment. I'll probably slip this in the middle of the video and replace the previous explanation I had because it was a bit not that great, but essentially hopefully the idea now is clear. In these new boosted coordinates we have to essentially use a different coordinate grid that's no longer perpendicular, and that's just going to change how we measure our points. And the really key thing to keep in mind is that you should stop thinking about the x and t axes, but you should rather think of the x-axis as a line on which t is constant and the t-axis as a line on which x is constant. If you use this logic when you move to these non-perpendicular axes, you're not going to get tripped up at all because you're just always thinking about lines on which a coordinate value is constant.